Hello, Eastview Scholars. Welcome to this edition of Sharp Shorts, where we're going to give you just a quick introduction to the periodic table. I have here just one square, and they all read the same thing. And let's point out a few things. First of all, the atomic number. That is this whole number that you often find in the upper right-hand corner. And by definition, that tells you the number of protons, which of course are in the nucleus and have a positive charge. That's what it is by definition, because the proton's job is to identify the element you have. That's really what it is. It's in the nucleus. It doesn't take part in reactions and bonding per se, although it has a certain amount of attraction. But it defines what the element is. So any atom that would have 19 protons would be potassium here, letter K. You can also assume that it's the number of electrons, because all elements in their basic state, before they react or before they bond or do anything, are neutral, which means they have to have the same number of positive and negative charges. The reason I say assume is this: proton number never changes. If that changes, the element changes, and the only way to change that is if the element is radioactive or goes through radioactive decay. But electrons, protons identify. Electrons are the worker bees. They do all the work, all the bonding, all the reactions, all the reactivity is based on the electrons. They're outside the nucleus. They're negative. They're in the electron cloud. And particularly the ones in the very outside edge, outside energy level, that are called the valence electrons. Those are the ones that do the work. So an element could, in bonding or reacting, gain electrons, lose electrons, or share electrons. But either way, that number can change where it can't with protons. All right. The other number on this square is the atomic mass. You can see here for potassium it's 39.0983. It's an average of isotopes that we're going to talk about in a minute. But by definition, again, the atomic mass is the number of protons plus the number of neutrons. Okay, that's the other subatomic particle. You've got protons that identify it. You have electrons that do all the work. Neutrons really define what form you have. If you remember from science, there's the term isotope. Isotope, by definition, are just similar elements, the same element, but they have different atomic mass. So really all they are different forms of the same element. I'll give you the very popular example. Carbon-12. This is what you and all living things are based on. We get our carbon. Carbon dioxide is in the atmosphere. Plants do photosynthesis. We eat plants, or the things that eat plants. And that's how we regenerate carbon in our system and get it back and replenish ourselves and remain a carbon-12 based thing. There's also a very rare carbon-13, and more importantly for this isotope discussion, carbon-14. Okay, and we have very small amounts of those. Again, we get them the same way from the atmosphere, etc. But like this is made by nitrogen way up in the atmosphere that's getting hit by cosmic rays and stuff and whatever. Anyhow, the point is, all of these have 6 protons, every one of them. What differs is their neutrons. Carbon-12 would have 6 neutrons. Carbon-13 would have 7 neutrons. Carbon-14 would have 8 neutrons. It gives them slightly different properties. And in archaeology, what they do is they look at the levels of carbon-14, because while you're alive and based on carbon-12, you're constantly regenerating carbon-12. That's the most prevalent one in our society. When you're no longer living as a living organism, and this is all living organisms, then that ratio and balance with carbon-14, since you're not regenerating, changes, and they measure that to see what's going on. Anyhow, the point is, that's what neutrons do. They tell you what form you've got. This number essentially becomes an average by percent composition of what those things are. You'll do a PhET lab and really work with that online. And the ones that are on the periodic table really illustrate the ones that are most prevalent. The last thing to talk about with this slide is the symbol, which is just the shorthand for what it is. Now, this is K, and this is potassium. Okay, and you say, well, there's no K in potassium. You're right. But that the Latin name does begin with a K. So generally, you'll get very used to, I'm not going to ever ask you to memorize the periodic table. What I'm going to tell you is get used to, understand what the symbols are. And I'll use the letter C. There's 92 naturally occurring elements. There's only 26 letters in the alphabet. C is very popular. You've got regular C for carbon. You've got CO for cobalt, Cr for chromium, Ca for calcium, Cs for cesium. What you can see, pun intended, is that it's either the first letter or one of the first letter and one of the first other couple letters, something that sounds like or gives you an idea of what that element is. Like I said, cesium isn't spelled CS, but S is the third letter there. There are some, like potassium, that still use the old Latin. Sodium is another one. Sodium is Na for natrum. Lead is Pb for plumbum. Gold is Au for aurum, but that gives you the idea. And the more you use it, the more you get used to it. For the rows and the columns, let's skip to a full periodic table here. The rows are what are the periods, and when I was just mentioning the electrons, and particularly the outermost energy level is the one where the electrons do their business, those valence electrons. Well, you can see here, the rows are what's called the periods. That's the energy levels. Okay, so 1 through 7. Francium, its last valence electron, will be out in level 7. It has to be. The nucleus is positive, the electrons are negative. Opposites attract, just ask my wife. But you can't pack all those electrons right next to the nucleus. The more and more you get, the more repelling the electrons will do to each other. So they're organized in these hypothetical energy levels. And the periods, the rows, tell you that. Okay? And there's a lot. You can see the periodic table is arranged by increasing atomic number and stuff. And there's more as we learn about electrons to how this is organized. But that tells you this. Here's rubidium. Its electrons, most outermost valence ones, will be in the 5th level. Lithium will be in the 2nd energy level. The columns are called groups or families. And you can see a listing of them here. Column 18 is the noble gases. 17 are the halogens. Here, starting with lithium, you have the alkali earth metals. Here's the alkaline earth metals. All that tells you is all those family members, those group members in a column, have similar properties. And the reality is it's because they have the same number of electrons in their outermost energy levels. So these all have one electron. This has one in level 7, one in level 6, one in level 5, one in level 4. That will give them similar properties. So that's the rows and columns. The last thing to look at in our periodic table is just by properties. We just got done working on properties and getting an idea of what some of the properties were. And here you go. Here's another. You can see how, as the periodic table is arranged, you've got metals, nonmetals, and metalloids based on properties. And they're kind of grouped together, as you can see. The majority of which are metals. Those properties help define how they react. They're not all the same. Here's the properties of metals and the characteristics. To me, the most important for you to understand is they like to lose electrons when they bond or react. But the idea is, while they're not always exactly the same, gold is the most malleable. You can pound that thinner than any other metal, but almost all metals you can hammer into thin sheets. How thin depends on the thing. They're not exact properties, but they're very close together. So that identifies some of the ways in which they'll react, and you can understand then how metals will react with nonmetals or with metalloids or with each other and what they can do, and that starts leading you to types of bonding and reactions they can have. Nonmetals, on the other hand, are almost the exact opposite as you read that, and look here. They tend to gain electrons. Okay. Metalloids are right here, a little column in the middle. The most popular one you know is silicon. They have properties of both. Silicon really found its way into computers because it can conduct, not as well as a metal, but it doesn't have the heat issues that would cause it to create problems. So when somebody figured out the properties that metalloid would be great for computers, the home personal computer world just exploded, and your phone now can do more than a whole building full of computers used to back in the day. Anyhow, that is our quick introduction to the periodic table. Scholar on Eastview